Okay. So now we found the critical point is the cube root of 15 over 4. Next, to find the minimum value. Okay, so here I will do this by using two different ways. First, I will use the first derivative test. So the domain of the function is divided by this critical point. Now the cube root of 15 over 4 is around 1.55 1.554. So we have two intervals. One is from 0 to 1.554. Another is from 1.554 to infinity. On each interval, I choose a test point. So here I use 1. Here I use 5. Okay. Now I plug each test point into the first derivative of the function. When w equals 1, the derivative is 40 times 1 minus 150 over 1 square. This is a negative, so the first derivative is negative. And when w equals 5, the first derivative equals 40 times 5 minus 150 over 5 square. So that is a 200 minus 150 over 25. So that is 194. The derivative is positive. And because we know if the derivative is negative, the function is decreasing. And if the derivative is positive, function is increasing. So from this graph, we can see that the function c of w has a local minimum when w equals the cube root of 15 over 4. Because since this is the only critical point on the domain from 0 to infinity, since cube root of 15 over 4 is the only critical point, therefore the function has an absolute minimum at this point. So to minimize the cost, when we design this container, the width should be cube root of 15 over 4. Therefore, the length should be 5 over the square of the width. Okay, now let's see what if we do this problem using the second derivative test? Now, to use the second derivative test, we need to find what is the second derivative of the function c of w. So I take the derivative here. We can have the second derivative is 4t minus 2 times 150. So let me first rewrite the function. Okay, let me write the function into this form. So, the second derivative of function is 4t minus negative 2 times 150 times w to the power of negative 3. So it's 40 plus 300 times w to the power of negative 3. Okay. After we found this second derivative, next we plug the critical point into the second derivative, and we evaluate the second derivative at this critical point. So let's do here. It's 40 plus 300 over w to the third, right? That's our second derivative. And since the critical point is the cube root of 15 over 4, and we said it's around 1.554. So we evaluate this function at 554. Now we can see the result is positive. Now this is positive. So this is positive. This means the function gonna be concave up at this critical point. So if function is concave upward, the graph gonna be like this. And since at this point the first derivative is 0, so we have a horizontal tangent line. So from this graph, we can see that the function has a minimum value at this number, 3, the cube root of 15 over 4. And since this is the only critical point from 0 to infinity, therefore the function also has an absolute minimum at cube root of 15 over 4. So to optimize the cost, to minimize the cost, the width should be the width of the box should be the cube root of 15 over 4, and the height should be phi over W squared should be 5 over the square of the cube root of 15 over 4, and the length, because the length is twice of the width, should be 2 times the cube root of 15 over 4. And let's take a look at this point, what is the cost? So if we are looking for the cost, we can use this function. We can plug the critical point, the cube root of 15 over 4, into the function. So that result gonna tell us what is the cheapest cost. And I already did it here. See, this is our function c of w. From this graph, the function has the minimum value at this point when the x, here x stands for the width, when w equals 1.55, when w equals 1.554, and the y value is the corresponding cost. So the cost is around $145.